backwards, not forwards. So we want to talk about what are thermodynamics. Well, thermodynamics refers to the changes in energy and state of a certain chemical or physical reaction. The main application for us as biologists or chemists is to track and predict changes of reactions or molecules. Like I mentioned, this is big. Thermodynamics is very important for engines and a lot of mechanical stuff that engineers or physicists might deal with. But because we're only talking about the MCAT, and mostly it's all about biology and chemistry, that's what we'll be focusing on, right? And that would involve chemical reactions or molecules. So the first and most important quantity in the universe is entropy. Entropy is essentially a measure of the randomness of a system or of the universe itself. And it's represented by the letter or symbol S. So the entropy of the universe can never decrease, right? The randomness or chaos of the universe can never decrease. It can only stay the same or it can only increase. There can never be a chemical reaction that occurs that will decrease the entropy of the universe as a whole. And when we say universe as a whole, we're talking about essentially everything, right? Everything that we know. However, there can be chemical reactions that decrease the entropy of a small system in the universe, and that's what we mean by system. A system is just a small part of the universe. So say you had a container, right? Small glass container in which you had some chemical, that you put in some chemicals and they underwent a reaction. Well, that small container would be a system in the universe, right? And everything outside of the container would be the surroundings. Everything that makes up the universe that's not inside the container is the surroundings, whereas the system is the actual contents of the container. Okay, so there can be chemical reactions inside that container that decrease the entropy of that container, but the entropy of the universe as a whole cannot decrease. So what that means is the entropy of the surroundings, so everything outside the container, as a result of the chemical reactions inside the container, must increase entropy at least as much as the system decreases, right? In order to maintain balance. And you can see that with the equation we have at the bottom. The entropy of the universe equals the entropy of the system plus the entropy of the surroundings, right? And that's because the universe is the system plus the surroundings. So if you combine everything inside the container, everything that's not inside the container, you just get everything. Okay. Okay, so how do we change entropy? So there are many ways that changes to entropy occur in a molecule or a system. The main way is through changes in state. So for example, a gas will always have more entropy than a liquid, and a liquid will always have more entropy than a solid. And you can see that over here in the bottom right with these molecule diagrams, which I'm sure you've seen before. So if you look at this, which is a gas, the molecules are very free to move around and bounce around, and they have many different positions or locations they can be in at any given point. Because of that, there's a lot of potential for random or different assortments, essentially, of the molecules in space. That gives a very high entropy. If you look a little bit to the left, you see the molecules of a liquid. You can see they're a little bit more packed together. They can still move around a little bit around them, but to much less degree. That means that there's many less potential locations or ways they can be arranged inside of the container in order to kind of like be random. So because of that, the entropy is less. If you look at a solid, it's completely rigid, completely tight. There's no movement, it's just rotation and vibration. Because of that, very little different potential for randomness. And because of that, it will have very low entropy. And this is pretty much always the case. Solid is less than liquid, which is less than gas, for entropy at least. So another common way to change entropy is through temperature. So if you increase the temperature of a molecule, you increase its entropy, and vice versa. If you decrease temperature, you decrease entropy. Entropy has units of joules per Kelvin. So you know that joules is a form of energy, and Kelvin is a form of temperature, is a unit of temperature, I should say. Increasing the temperature increases the kinetic energy of the molecules, right? So if you want to go back to this diagram, You notice how the gas molecules are like, they have the arrows, which means they're bouncing around inside the container randomly. If you increase the temperatures, you increase the kinetic energy of the molecules, which means you also have to increase the speed that the molecules are traveling, which means the molecules will move even faster around this container, right? And that's would increase the energy, which would increase the joules of entropy, right? So if you have entropy, and the numerator of entropy is joules, and the denominator is Kelvin, with increasing temperature, you do increase Kelvin, which would make entropy smaller, but you also increase joules by an even larger amount, an improportionally large amount. And because of that, you actually end up increasing entropy, okay? Like I mentioned, entropy itself usually has units of joules per Kelvin. However, delta S, or changes in entropy, especially of a reaction or a small system, usually has units of joules per Kelvin per mole, right? And that's because most of the chemical reactions we look at are on a per molar basis, right?